So let me please introduce Jun. He is a faculty in the Department of Mathematics, also in Okonomitsu University in Tokyo, Japan. Jun has been working on knots and primes for years. And this time he's going to give a talk about a joint work with Nadav Groper from University, Pennsylvania University and also Haifa University, and Yi Wang from University of Illinois. And the title of the talk is Anabelian Geometry in Arithmetic Topology. Please, June.
Thank you for introduction. I'm going to talk about Anabelian geometry and arithmetic topology. Several years ago, maybe 5 or 6 years ago, I gave a talk about Chebotarev link in Kiev. And this is continue. And today's talk is a continuation of that former talk. First of all, I would like to ask a quiz for maybe for undergraduate course students. How do you want to prove that square root of 5 is not contained in this field, rational this field? Maybe there are several answers, but I perhaps Hilbert ramification theory is a good answer to capture that situation. For example, let us consider this extension, quadratic extension. Then we have an extension of the ring of integers. And in this extension, prime ideals behave in 3 different ways: decompose, branch, or inert. Similar phenomenon we can observe for 3 manifolds. Let us consider a double cover of of the 3-sphere, branched double cover of 3-sphere, and let K be a knot in S3. Then we consider the inverse image of the knot. Then sometimes it decomposes into 2 components. Sometimes it inert, and sometimes it branches. Branches means that the meridian forms a double cover. Inert means that the covering degree is 2. This is a typical analogy between knots and primes, or numbering, 3 manifolds and numbering. Here is a bit more dictionary between knots and primes. And we focus on extension, a branched extension of number fields and a branched cover of 3 manifolds. And they are both controlled by the fundamental group of exterior of the branch locus. And we also have the analogy between local theory. These are periodic integer ring and the residue field, and the ring of periodic integers and ring of the field of periodic numbers, and the residue field, a finite field, corresponds to tubular neighborhood and the boundary of tubular neighborhood and the knot. We have an analog of class field theory, Iwasawa theory, Hidameza theory. Especially, we have an analog of idyllic class field theory that sums up all local theories to describe global abelian theory by fixing infinite link in a 3 manifold. Here is a bit more about Hilbert ramification theory. Let H be a finite branched Galois cover of 3 manifold, and let K be a knot and K prime denote the inverse image of a knot. Then the decomposition group and the inertia group of this K prime are defined in this way, and they are a quotient of Z2 or Z. They are generated by longitude and meridian or just meridian. And we have the sequence of subgroups of the Gara group, and they correspond to the subcover of uh, the given cover. And the first part, K prime only completely branches, and the next part, K prime completely inert, and the last part, and K prime completely decomposes. Um, in next, in this context, one of the fundamental question is uh, about the analog of the set of all prime numbers or all prime ideals. Uh, it should be a link consisting of infinitely many tame components. And there are several good candidates of conditions for this link. Chebotarev, stably generic and very admissible. If there is an implication between among these three conditions. If we assume this link is very admissible, then we can formulate an analog of idyllic class field theory. And if we assume Chebotarev, and then we we can study an analog of Anabelian geometry that I will explain in this talk. One of the most fundamental result in Anabelian geometry is so-called Noikirchi-Uchida theorem. Let E and F be a finite extension of rationals contained in a fixed algebraic closure of the rationals. If there is an abstract isomorphism between their absolute Galois groups, then there uniquely exists an element in odd Q bar such that F equals sigma E, and this sigma induces the given isomorphism phi. And this is one of the very starting point of the story of Anabelian geometry. So if we can formulate an analog of this theorem, then we will find many things to do after that. And the key portion of the proof for this theorem is Hilbert ramification theorem and the Chebotarev law. So we are almost we can feel that we can almost approach this theorem. This is one of the key lemma, but um, I explain. Let f over q be a finite Galois extension, and let e over q be a finite extension. If a prime number p has a prime factor of degree 1 in e over q, then P completely decomposes in F over Q. If this extension satisfies this condition, then F is contained in E. This is a key lemma. And a typical step for the proof of the Noikiri-Uchida theorem. Um, and we have a more general theorem called Bauer's theorem, and probably we can formulate that also. Next, I will explain topology, more on topology. First, we need infinite Galois theory, Galois theory for infinite cover. Let M be an oriented connected closed stream manifold, and let L be an infinite link with stem components. And let us consider the set of all branched covers with base points branched along finite sublink of the fixed infinite link L. And let us define an analog of the absolute Galois group by the inverse limit of all finite branched covers. The Galois group of all finite branched Galois covers branched along this infinite link. Then we can formulate an infinite version of Hilbert ramification theory. So if we fix a system of knots in the system of covers, then the decomposition group and the inertia group are defined as the inverse limits of these and each layer, and they are isomorphic to z hat to 2 or z hat. Here z hat denotes the profinite compression of z, or the inverse limit of z over nz. Next, we will recall the definition of the Chebotarev link. And let Ki be a sequence of disjoint knots in a three-manifold M. And for each natural and non-positive integer n, let Ln denote the union of Ki with I less than or equal to n. And for each j greater than n, let kj bracket denote the conjugacy class of kj in the exterior of Ln at the fundamental group. We say that this sequence Ki obeys the Chebotarev law if for every n and for every surjective homomorphism from the fundamental group, the exterior of Ln, to any finite group, and for every conjugacy class C of G, the following equation of density holds. Here, the left-hand side is the natural density of knots that hits the fixed conjugacy class C. And we have a theorem that assures that we have an example of Chebotarev link. This is a result of Macmillan. Let A be denote the matrix 1, 1, 1, 2 acting on the torus. Then it also acts on the torus minus the origin. Then its mapping torus is homomorphic to the exterior of the figure 8 knot, and we obtain the so-called suspension flow. And its closed orbits and the figure 8 knot obeys the Chebotarev law if they are ordered by length. This is Macmillan's result. We remark that the inverse image of such link is again Chebotarev in any cover, any finite cover. Uh, mm, mm. Now I will state that main theorem, the Chebotarev-Uchida theorem for three manifolds. Let M be a three manifold endowed with a stably Chebotarev link. Let G1 and G2 be open subgroups of the absolute Gala group. And let H1 and H2 denote the covers corresponding to these two groups. If there is an abstract abstract isomorphism of topological groups G1 to G2, then there uniquely exists an element of Gala, the absolute Gala group, such that H2, the composition of H2 and sigma is H1, and this sigma induces phi. This means that if we have an isomorphism of groups, then we have a natural isomorphism between the corresponding coverings. And we have a similar lemma, and that plays a key role. Maybe I should remark that this Gala group is the inverse limit with respect finite sublink of L of the profinite completion of the group of the link exterior. So this story is closely related to the story of profinite rigidity. But usually in the problem of profinite rigidity, we study the profinite completion of finitely generated legendary finite groups. In this case, we consider very large groups, so it's a bit different, and perhaps this will give a new viewpoint. Um, uh, I'll stop here. Thank you.
Okay, June, thank you very much.